The Marshall family was no ordinary family. Rick Marshall, a brilliant scientist passionate about exploration in the unknown, had decided his life and dedicated all of his efforts to studying time and space anomalies. His expertise and groundbreaking research caught the attention of a clandestine organization known as the Temporal Exploration Agency. As fate would have it, the Marshall family arrived by raft at the designated spot just as a massive earthquake triggered the portal to open, which materialized and manifested as a whitewater whirlpool, completely enveloping the entirety of the Marshall family. Its swirling vortex seemed to beckon them as if it was meant to be all along. In an instant, the family found themselves transported to a world that defied all logic and explanation, the land of the lost. The time portal had functioned not as a mere gateway to another time, but as a multidimensional portal that had inadvertently drawn them into this prehistoric realm. Rick knew they must find a way out back home, and to do it, they would need to hack time and space itself. Euclidean geometry claims that for any two distinct points, there exists a unique straight line that connects them. Every pair of points in Euclidean space has a unique positive distance between them and a straight line segment that can be extended indefinitely in both directions, creating an infinite line. Since the discovery and mapping of the universe using cosmic background radiation, modern cosmological topology considers these notions at best naive and at worst patently false. How has humanity defined the truth of space and time using maps and machines to track time? Does Euclidean reductionist thinking limit the mind's ability to experience the possibility of more complex timelines and topological structures for the universe? How have religion and mysticism looked at time and space as a non-linear repeating forever now? Welcome to episode 8 of The Richest Family, Orobos, the End of the Universe, and non-Euclidean typologies, where we talk about cartography, chronography, the land of the lost, and other questionable geometries. Hey, guys.
What's up?
Hey, Clay.
What's going on, guys?
What's up, Greg?
How's it going?
What a pleasure it is to see both of you.
Oh, yeah. Oh, yeah.
After a weird week, we're going to have Jim give us a little disclaimer because something we already know.
So this disclaimer is going to be a little bit different since we're talking about suspect geometries. Let's put this disclaimer into terms of kind of a 3D, 4D, 5D, 6D fractal. So basically, our bullshit has bullshit inside of bullshit with little tiny, and then it keeps going. And so you'll be flying through a space, and then suddenly you're inside of some other bullshit.
There's many leaves of bullshit.
Yes, exactly.
And the leaves have smaller leaves.
Yeah, that's exactly right.
And they're not all brown.
No, they come in all shades, and in fact, a lot of them are outside of the visual spectrum of light. They might be very low frequency.
They're infrared.
Oh no, it goes into the radio wave spectrum here.
Microwave.
Oh yeah, they're bigger, okay. Like radio waves. But then some of them are very piercing, like gamma.
Oh
yeah. Oh yeah. Like, ouch! What was that? Oh, that was some piercing bullshit.
There's actual stars emitting giant streams of bullshit.
Yes, that's our disclaimer for the day. So that's what we're up to. But on the flip side, I think that there's some very interesting conjecture. In the tradition of Leonard Nimoy and other former members of the Star Trek cast.
Well, I mean, this topic is, for me, it's something I always, whenever I watch PBS Space Time, which I fucking love.
It's awesome.
I think about some of these things, which is like when I learned that, first learned that the universe was expanding and that it was accelerating, it kind of terrified me because it made me think, oh, well, what? Will it just everything just go apart forever and end? You know, like, is there no chance that our universe might have another chance to be reborn? And like, you know, some of the things we're talking about are about that. But to even get there, we had to start by even understanding space and time. I mean, we've gotten pretty advanced, and it started pretty early with just being able to create maps and to track time.
Well, one thing that I think really makes this a perfect subject that connects with our previous talks is how it seems like such a fundamental, immutable concept. Yet, when we look even just at the recorded history that we're able to look at, our perception and uses of time have changed so fundamentally, and certainly over the last, couple hundred years, that it's in a way it kind of doesn't make sense. You're like, well, if it's such a constant, immutable part of everything now, why wasn't it back then too?
But time and space,
and that's
right?
what we're exploring, and that's what we're exploring.
It's time and space. It's like understanding
Absolutely.
how the
Our
world works.
perception is so much the same.
You've been looking into a little bit about like some of the history of time and space, haven't you?
The measurement and perception of time have evolved significantly throughout history. Initially, humans relied on natural events such as the rising and setting of the sun, the phases of the moon, and the changing seasons to understand the passage of time. However, as societies progressed, there was a need for more accurate and standardized ways to measure time. This led to the invention of clocks, which had a profound effect on various domains. The invention of clocks revolutionized scientific research. Prior to clocks, science had limited means to measure the duration of experiments or observations. The introduction of precise timekeeping allowed for accurate data collection and analysis. Scientists could now measure the duration of chemical reactions, observe celestial events at specific times, and conduct time-dependent studies. The advancement greatly enhanced the efficiency and reliability of scientific research. Clocks also played a crucial role in the development of transportation. Before their invention, travel relied heavily on natural cues and estimates of time, afternoon, noontime, dusk. The introduction of clocks allowed for the scheduling of transportation routes and the synchronization of departures and arrivals. Ships, trains, and later airplanes started to adhere to specific timetables, enabling efficient and reliable transportation. So originally, people's perception of time was mainly like now, and not now. The idea of tomorrow or even something earlier it was an immutable thing. It was something that was not necessary. But then you have like perception of day and night, time when we're asleep, time when we're awake. And then you have periods of time when the sun was not necessarily visible for long periods of time. There was volcanic activity. There was a time period in the Middle Ages where the sun wasn't visible for decades, and obviously the crops suffered from it. And we're kind of seeing that like our perception of time has evolved as our need for time increases. Suddenly if we're working for someone else, then it's like, oh, we have work time or play time. And that's when we come into these ways of dividing up the day, as opposed to just, oh, if there's light, we're working. If there's night, we're sleeping. And the day was measured differently in the summer and the winter because they didn't necessarily have an accurate way of saying, oh, this is a duration. They would just say like, oh, midday, and then chop that up into 6 parts.
But wasn't even time, it wasn't, these kind of same methods used to, and when we're talking about like how people understood the world, these types of things were used to be able to move and track like human existence, like the day, the light centered day, and how much could be accomplished in a day.
Well, but see, that level of planning wasn't achieved until a certain point. Like hunters and gatherers are not really going to be as dependent on the cycles of the local fauna and flora, because they could just burn out an environment and then move on.
Well, this
Whereas
became the priesthood, right?
right, once you start getting a custodianship of land, then you have the observation of the natural cycle so as to optimize that custodianship. Like you see in Stonehenge and Newgrange in Scotland, they were observations of the moon and the stars to see these sort of longer cycles, longer than years.
Right. So they're using like, then that's where like the Stonehenge and the, now you're tracking celestial
but even
tracking, right?
yeah, but even looking for these things wouldn't have had a meaning until you had a society that had a need for this information. Like that's what I'm saying is the hunter and gatherer would not need as much of this cyclic seasonal information as a farmer would.
One thing I'm noticing here a lot, and I think it comes up in our theme, is if you look at these pictures, almost all of them are a circle or a semicircle, and even the half circle is indicating a circle, right? It's indicating a loop of some sort, right? And just because you're seeing half of it, that means, well, I'm only dealing with half of the day. The other half, I'm unconscious, right? But what it's implying is that for that there's a loop, and I think that's an important thing. You see these circular forms and all of these kind of early chronographic representations.
Well, see, even to observe these circular trajectories, we have this sort of dichotomy between like the wave and the particle. It's like, okay, your snapshot of observation is just that one picture you've taken to sort of digest in your brain and understand it. But the phenomenon has kept going since that snapshot. So you say, for instance, like a hunter, trying to shoot an arrow at a moving animal. He's seeing where the animal is while he's aiming, but in his mind, he's also visualizing the trajectory of that animal's movement, having to add that into his aiming formula. And that's what our perception of time becomes.
Because, the arrow of time.
Because we just have these sort of snapshots, but then it's our brain's ability to extrapolate on the patterns
and that
create the continuity.
Our whole POV concept, right? So what about space, though? I mean, like, we're talking about 4 dimensions here. Like, when we experience like Euclidean, it's a grid. The grid has one aspect of it, which is time. Things move through time. The other Euclidean aspect is space itself, right? I mean, like, and that's why people start making maps, even though maps are 2-dimensional, because we're moving over a sphere. It's handling this traversal of humans through space.
Because certainly a lot of our perception of distance was measured in time. I mean, even still, we talk about things being a 10-minute drive rather than it's 1.4 miles.
Sure.
Because it's more of our truer perception. I mean, I might not perceive the distance unless I looked at my.
We've had maps for a long time, and maps don't try to capture that.
Well, there is this map, existing map from Rome that it was a map of their road system. And they had, certainly like the where to split off, what the conditions were like, but it was measured in days of March. Like in spring or in winter, they would say like, okay, in winter it's icy. But that was how it was, along with the actual distance, was the time necessary to traverse the distance. Maybe it's uphill or, some perceived measurement.
So are you saying that early maps, are you saying
at least this Roman one, because it's mainly meant for land travel and not so much for sea travel.
Right. So are you saying that early mapping was just as much, or even the way it was represented was in distance by travel?
Yeah, because that was the way it was perceived, and that was an easily understandable way for everyone doing it to understand it. It's like, oh, it's midday, we're halfway through this, day's segment, and because they have to think of the logistics of like, oh, breaking for lunch, it's like, oh, we got to get this pack animals over a mountain. Is it better to wait till the next day? Just like when you look at mountains that have been climbed quite often, they have specific points where they're setting up base camp, or places to observe the weather, to wonder if they're going to go to the difficult pass. And these were built into these Roman maps, rather than just the specific. And also, they weren't necessarily, like, if you looked under like a bird's eye satellite view, they'd be like, this map is not representing this, But
Interesting.
when you're on a road, you're just walking, you're just following the road until you're seeing landmarks, whether I'm going slightly west or slightly east, diverting from a true direction is less important as long as you're on this road.
So early maps were different than modern maps. I mean, like, if we think about the changes, it seems like to me some of the changes.
Ptolemy.
Oh,
creating the concept of longitude and latitude. Because previously maps were, just a path. This is what we saw on the path. Or as people got better at cartography, you would get coastlines. And that was really like all of our, like these later maps that we see of all the world, like the Pyrie Reis maps. These were a compilation of coastal maps made by captains and
wait.
guarded secrets.
I think we dropped one thing here. Is the big thing that happened? And you said longitude and latitude. That has to do with a ball as opposed to something flat. So a big change here is the change between something like a flat Earth map, a fantasy Earth map,
right, based on
and something that's on the ball. Because as soon as it's on the ball, we have to reproject it and do weird things to try to rationalize it.
And the reason that is that we need to have navies to use that map instead of people walking. And so that's where longitudinal projection actually becomes important, because if you don't have it, ships start going fucking to the wrong place. They start, you know.
Yep. And there's something else. Like initially you had we were talking about time and how people kind of encapsulated that. Well, a major thing was there was kind of a monopoly on certain elements of time by the priesthood, because they were the people who looked at the stars. In certain civilizations, you weren't really allowed to look at the stars and make predictions or any of this stuff. And so this group of people figured out that there were objects that were wandering around. Those were the planets, and that the stars were moving. And they could look at where these things were in the sky and make predictions about when the floods were going to come in from the Nile or whatever, right? And so if you're talking about the Navy, Clay, as soon as you combine the cartography with the astronomy, then you've got the time and the location starting to gel together.
And before they figured out how to make clocks, that's exactly what they did, right? That's how naval navigators figured out. But it's still super difficult to figure out longitudinal navigation with the stars.
Right, that was the astrolab, the development of the astrolab that enabled that. Yeah, previous to that, it was just latitude and coastlines. And even that would become problematic in cloudy weather. Just knowing where the sun was the Vikings had this thing before they even had compasses, and it was like a translucent stone that they would look at the sun at a cloudy night through, and it would diffuse and allow you to identify where the sun was. I mean, now it doesn't seem like much technology, but to be able to navigate when other people couldn't was certainly an advantage that the Vikings took a big advantage of,
But still, I mean, like, my understanding is there were a number of very large naval disasters where ships would run into like rough, they'd run aground and not know it because the maps were not, they couldn't accurately navigate because they didn't have longitudinal navigation. And so here's where this connection of time and space connects is in navigation, right? Because you can actually use a clock to determine your longitudinal position. And so that to me is this really interesting connection. Like, wasn't there even like an award, like the Nobel Prize of its day?
Yeah, there was that accident in where were you saying, Spain or Portugal? Where these ships are unable to dock accurately because of their lack of accurate time measurement, and I guess they miscalculated the tides, and they wrecked a bunch of ships. So the shipping company made an award to said we need a clock that is accurate on a ship and is not using counterweights or the movement of water, something that's going to change as the ship's moving. And it was either a Swiss or a German watchmaker, and it was a variation of something that existed
I think his name
already.
is John Harrison.
Okay.
Yeah.
And it was a spring-powered clock, but just one that was able to maintain an accuracy of it. And this is, of course, dependent on the development of materials that could maintain a constant tension for this.
I guess we are out at sea and, the ship's moving around. You have to isolate the clock. I mean, when I'm looking at this picture, it kind of looks like, there's this thing in a box, and the box has like the ability to move freely inside. So if a ship is moving, the waves are coming, it's able to actually isolate all that and maintain its, clocks are pretty intricate technology. It's able to maintain that so that the navigator has a clear understanding of time.
Yeah, and a major factor in that particular design was you've got a spring. The spring needs to have a certain amount of continuity in its ability to retain energy. And so there were regulation. The big innovation was being able to regulate that tension inside of the clock so that even when the spring ran out, it still kept the clicks happening at the same speed. Right.
And they had to figure all that out for gravity fed clocks, gravity powered clocks too, right? Because as the pendulum moves down, it has different tensions, or it seems to me that like all the clockmakers were trying to solve the same problems at the same time around the 1700s, early 1700s.
Yeah, and so this became metallurgy in Germany, right? Because that spring making process became like a super secret.
Yes, to be able to make process. That spring steel. Yeah.
Yeah.
One thing that I think is interesting is originally the measurement and perception of time is the relative movement of the sun and the stars. But as you start getting into clock making, the use of quartz, the measurement of it starts to be more accurate than the phenomenon we're supposed to be measuring. Leap seconds, leap years. The year is not a perfect 360. And I mean, now I think the standard for time measurement is the decay of cesium.
That's right.
Yeah, have you ever listened to the atomic clock?
Yeah, it's just some kind of, super regular buzz that I'm going like there's variations, in the moon's orbit, the sun's magnetic pull that are creating these fractional variations that, suddenly our measurement is more accurate than the thing that we're measuring.
Not only that, now that the atomic clock and the ability to track time at that level is basically proved out relativity, because when we started putting satellites up that are completely dependent on longitudinal positioning for geosynchronous, they are moving at a speed relative to the Earth because they have angular momentum that puts them out of sync with the Earth's clock. So these GPS satellites were constantly tracking longitude incorrectly, and they actually had to
Do
have
relativity adjustments,
based the relativistic effects, right?
Yeah.
So relativity, the theory of relativity, was actually proven out by an atomic
Observation.
clock. Right, that's right. So it's really interesting, this connection, especially on the longitudinal aspect of the Earth. But I want to transition that a little bit, because we can look at it from an Earth level, but now as we become, a next level, a first order
standards outside the solar system,
we start to look at, and especially with relativistic effects, we start to look at, well, what happens when we think about the universe having different topologies also, right? We thought the world was flat, and our measurements helped us figure out that it was actually round, and we did that through the thing that helped us figure out that the Earth was round was actually the same stuff we used to do time. It was shadows and poles sticking up, right? Yep. So now with the cosmic background radiation, we've actually started to understand how the universe works. And we thought that it was just noise, like the guys who figured out what the cosmic background radiation were. They were using this big horn telescope, and they were pointing out at the sky, and they were like, shit, there's all this noise that's fucking up our signal. And they went out there with like brooms to try to push all the pigeon shit out, and they were still getting it. And actually, the more they pushed they cleaned it, the more noise there was.
The bug is the feature.
And they figured out that the universe was decaying, and that the cosmic background radiation was basically a snapshot of decayed light from the very early universe. Okay. And it allowed them to start actually mapping the topology of the universe. Actually, the way they figure out what the shape of the universe is through something called omega, which is the ratio of the actual, what is observed more. Actual is a really crazy term in science.
Bent light rays and stuff.
Well, but they don't, when you say actual, it's like what we think is actual at this moment in time.
Yeah.
But what's observed, the density relative to the critical density. And so using the cosmic background radiation, like the measurements that they've been, and now they set telescopes up just to measure that, there's 3 potential topologies of the universe. There's the one we all think of today when we talk about stuff, which is the Euclidean one, which is, almost like Newton. There's this stage of space and time, and it's basically flat. Then and so in that pattern, the omega is equal to 1. The density in the observed is exactly the same. Then there's a saddle universe. And the saddle universe is where the actual is greater. I mean, that is less than the critical density. And then there's a spherical one where the actual is greater than the critical density. And so in these 3 topologies, the fate of the universe is held. In the one where it's flat, the universe could just go on forever. It could be expanding and it would never change, accelerate. We'd have heat death. And heat death is like the universe just dies.
Dissipating.
Slowly, trillions and trillions of years, but all the stars go dark. Everything becomes black holes. The black holes then decay using Hawkins radiation. Jim wants to say something.
There's one other. Speaking of black holes, there's another one that's kind of weird. That is a very talked about. I mean, people are actually postulating that this might be what we're looking at. That when we're talking about the universe being flat, it might actually be flat. As in a 2-dimensional.
Oh, it's not 4-dimensional. It's 3-dimensional in that it's 2 dimensions and time. projected.
But here's the kicker.
Right.
It's actually a projection on the surface
Of a black hole.
Yeah,
I've heard that.
Oh, geez.
Yeah.
Well, no, the guys that are postulating,
There's math.
It's hardcore, and
Yeah.
the craziest part of it is the emergent concepts of dimensions, things like 3 spatial dimensions. The third dimension is actually a projected illusion inside of this theory, which is mind blowing.
So
We're all extruded.
All I'm saying here is that, a lot of these concepts, and it's hard to tell whether it is our human brains that went through this whole chronological, topological process on Earth that we're projecting it onto the universe. But a lot of the second possibility is where omega is greater than 1. And that's the spheroidal one. And that means that it's a closed loop universe. And it doesn't mean that you could necessarily get back to the same position if you drove fast enough and far enough. But what it does mean is that the universe won't expand forever. And it eventually will close back in on itself. It's inevitable that it will, as it expands, it will expand into density and will be what they call the big crunch. And the big crunch is interesting to me because it essentially becomes a episode of Land of the Lost. So I don't know if you've ever watched Land of the Lost. When I was a kid. It was the go-to, and I think Larry Niven wrote for it for a while. Jim, do you know the story on that?
Oh man! Well, they had all kinds of.
They had some heavyweights. Yeah.
Yep.
And I loved that show. I was a freak for it when I was a kid because it had all these really cool concepts. Right? They had these pylons. They had the slee stacks and ancient civilizations, like Enoch belonged to this ancient civilization. But my favorite concept of it was the pylons, because there were these different kinds of pylons. There was the mountain pylon, the time pylon. And in one episode called The Pylon Express, there's the keyless pylon. And so what a pylon is it was created by a precursor civilization, and no one there's never any illusion of what that civilization was.
There is an episode where what I call future Chaka shows up, and future Chaka has a discussion where he says, oh yeah, this is basically, you might become like us one day, that kind of thing. And the idea is that the Land of the Lost might be an amusement park for a alien, because we were talking about this at one point, Clay, that Land of the Lost is a pocket tiled universe, right?
Right. And so
a couple Star Treks with that concept.
Well, it's a tiled universe that's controlled that can be experienced by entering into the pylon and using the matrix table. And so that's what happens to Holly. She goes in and she starts playing around with the matrix table. Don't play with the matrix table.
Don't play with the matrix table.
Hey, man,
have you ever had to rotate? Have you ever had to rotate a screen in code, right? Exactly. And you got that matrix table, and you're like, don't mess with the matrix table.
But
if there's a red button that says "Do not touch," what the hell, man? You gotta push that button.
Well, they're all red buttons on the matrix table.
Yeah.
Some are a little bit more yellow, some are red. But anyway, so she's in there and she's going to the snowball universe. and she's going to alternate altrusion universes where she sees unique. So I don't think that. So this is my belief system on Land of the Lost. This is ridiculous that we're doing this, but what I think is going on is the matrix table is basically the pylon doesn't move. What happens is that it shifts different universes in and out at the same point. The pylon never moves.
That's right.
And it's a matrix tiled universes. It's a multiverse.
Well, they're boxes. All those universes
right.
are like little boxes.
Right.
What's funny is that it goes to our universe.
Sure.
As well.
Yeah.
Well, because there's plenty of stages at which they're just observing. They're inside the pylon. They're looking out the door and they're observing, but not observed.
Right. Until they poke their head out.
Yes.
Right? And there's one point Holly could have even gotten out of the pylon and gone back home, but she didn't.
They threw a frisbee in.
I can't sleep, Dad.
Well, that little jumpy creature, with the fuzz balls.
Yeah.
Boing, the bucket, the fuzzy bucket.
Well, what happens? So why am I going through all this? That's super cool and it's really relevant. But the most relevant thing in my mind is season 1, episode 17. And it was really genius. Larry Niven was a writer on this. They didn't think they were going to have a second season. So they wrote this episode where to create a causal loop, to end the causal loop, and to get back home, they had to leave. And Enoch was kind of like, that would be irresponsible to do it incorrectly. And so they agree and they work with Enoch to leave the universe, but another family comes back in at the exact same time loop. So now the fate of the family is forever. It's a loop that never ends, this causal loop. And I just think it was really smart how it's done, because to me, that really relates to like a lot of the mythological cycles out there.
You know, what I'd like to think about, especially with Land of the Lost, is the time period that it's coming out and what culturally was going on while this was coming out. So in a way, there is so much visual ideology that is used in Land of the Lost that required no explanation because of the time period we had, like ancient aliens, pyramids, holograms. You don't need to say anything about that. Everyone has got their copy of Eric von Däniken book, Chariots of the Gods. Everyone had a mood ring. Everyone had some kind of pyramid in their house. So it's just taken this vocabulary that is just so much a part of pop culture and is the foundation of the New Age movement, was all these kind of like silly sort of post office paperback mythologies put together.
Oh, and Devo.
Yes,
you can't forget Devo, because one of the things that they bring up is they ask Enoch at one point, if I remember correctly, it's been a while since I've seen this, but I believe they ask Enoch if he's from the future, and he's like, no, I'm from the past. These creatures that you see here now have fallen into barbarism. We were complete. The Sleestacks are their descendants.
But I want to go back to this idea of how Land of the Lost loop was this time loop thing, and mostly because when I look at a lot of religions and a lot of mythological systems or belief systems, this concept, this loop, universe is very, very prevalent in it, whether it's in Buddhism with reincarnation. Hinduism is that's the Yuga cycle. And there's in the Yuga cycle, which is really interesting, it actually is all charted out how many years are in it. And the whole universe essentially is like originally what I was talking about, where omega is greater than 1. It's a big crunch. It expands. The universe expands.
Cyclic.
And then it comes back together in cycles. That's right. Same thing with the Aztec. We're in the 5th sun of the Aztec calendar. And so when you talk about the number of suns, what they really mean is how many times the universe was destroyed and recreated, and the sun and the moon was recreated. And in the hero's journey, Jungian and Campbell, the whole idea of the hero is the hero goes through the cycle and then creates another hero who goes through that cycle, right?
Well, I think that is one of the strengths of civilization able to make these long-term observations. What the Farmer's Almanac, what happens after 20 summers, because people are able to draw conclusions that are beyond the ability for one person to observe. And I think that's really the huge tool making advantage of the perception and measurement of time.
Mm-hmm. Well, I mean, ultimately, this gets back to one of my favorite symbols of all, and that's the worm of Orobos, which is this, this animal that is magical, that's eating itself and by its own tail. And as it rolls and creates the universe. It's like, to me, I actually, the Orobos is probably the next tattoo that you're going to be giving me, Greg.
Way to go.
And Jim gave me my first Orobos. So that's, to me, that's kind of what this is about, is how do things loop? How do they loop in on themselves? And Jim, you've been looking at like loops and loop systems and loop geometries. I mean, kind of similar to the cosmological topologies I was talking about.
Yeah, and one of the crazy things is just a twist in a loop creates a completely bizarre set of precedents geometrically.
Well, I remember this really cool show called presentation called Not.
Where, I was going to say not.
Yeah, right when it basically, the moment you take a rope and you tie it into a knot, all these really incredible math problems just instantly open up. And it's essentially what happens in a Möbius strip.
Oh yeah, and there's some crazy stuff. Not had an interesting thing that always stuck with me, besides all its crazy geometry, that a knot's mirror is not the same as the knot. That's why it was not.
Oh, very nice. Well, so, that's like a square knot versus a granny knot,
Oh, no, it's even weirder. It's like a knot is actually defined as it has to be looped. Like a knot that we have tied.
Has the rope.
It's not an actual mathematical knot.
Like a hypertorus. Or what is it? It's a primitive in Max.
Yeah. Exactly. A lot of 3D programs have primitives. I just wanted to do this super quick and take some interesting an interesting case study, and that would be the relationship between the Möbius strip. I mean, I think that as kids we all did the thing where you take a strip of paper, give it one twist, tape it back together again. Sometimes that strip had a line drawn in the middle. You cut it through the middle, and you have two links,
and it just goes.
And that's a very strange thing to see something that we don't relate to as having all these separate identities.
Oh, not only that, we'd always get a pin out and okay, watch this. Cut it, run the pin, and it would come back to its original point.
Yeah, that's right. Yeah. That's right. Well, something very strange happens. The obsession with it. So as they travel around, you can see how the surface, right? So people have tried to build, I guess they have built, but people have tried to build roller coasters that have dual tracks on them.
Oh, that's just going to make me vomit, man.
Oh, yeah, where you see people on the other side. right?
Oh man, is this like
So-
one
so
of those
this is an
euthanasia
obsession.
coasters?
Yeah. Well, okay. So then there's this other thing that has to do with the way that okay. So if you take a Möbius strip and then kind of extrude it out, maybe even relate it to another one, you end up with this form that's called the Klein bottle. Right? Have you guys ever
So a Klein bottle is
Sure.
almost like a 3-dimensional Möbius strip kind of.
It's
Yeah,
actually
but-
4-dimensional.
Yeah, glass blowers have faked them, you know,
They faked them.
because you're
Well,
not because they still the thickness of the glass, so it's not an actual representation of the concept of the Klein bottle.
You can't do a real Klein bottle because they actually exist as 4-dimensional and this is the thing. 4 spatial dimensions. It's not like height,
not the
width, and
time
depth, and
Yeah.
it actually is supposed to not intersect itself when it goes back through. And the relationship is that it has a relationship to a cylinder and to a torus and to a Möbius strip. It's just that its gluing order is borderline irrational, right? It's like it has the same relationship. It's being made out of the same
But it's
initial
possible.
rectangle, but slightly impossible with our understanding of spatial geometry.
But that is the kind of wonderful thing about evolution. Like even look at human anatomy. Some of the arrangements of our nerves, they're not created with a systemic, like, well, how do we build an efficient machine? It's just like, well, this evolved and then this sprouted off and then it came back down. And that's, in my estimation, how the Möbius strip existed. It just, things are moving and twisting. Oh, okay. It works. It doesn't have to make sense. It just clicks and works.
I think that it exists simply to give H.P. Lovecraft ideas about people going insane. And then they saw Cthulhu's geometry and they went irreversibly mad.
Well, like a possibility I'm thinking of, like, okay, molecular bonds, you know, when looked at the molecular level, are these shapes that are able to fit together. And that's what enabled different chemicals to connect or not connect. Now, once we have AI creating like artificial shapes to interconnect, it doesn't necessarily have to be just these noise patterns that happen to fit together. But like we're saying, these like extremely improbable shapes that do work, that are like forced into the system.
You know, Greg, I was gonna totally mention this while Clay was talking about the worm of Ouroboros, and that is this guy named August Kukule, who was a chemist who, during a dream or a daydream, or he was huffing benzene, perhaps. I don't know what was going on, but he was trying to figure out the chemical structure of benzene and had a dream about a snake swallowing its tail, and then realized that its bonds were in the shape of a hexagon with a specific kind of hydrocarbon structure, right? That's a circle, right? So sorry to sideline you, but I was just
no, but that's it exactly. That's it exactly.
Ouroboros without talking about
but
the benzene.
But that's what I'm saying. These patterns are going into every fabric. You know, like you break, you know, you take something, you shatter it. You're going to see the patterns that held it together.
Well, I want to, like, the interesting thing about the Klein bottle is, we were talking a lot about this, about projection systems and in-dimensional projection systems, like the idea that our 3-dimensional universe may be a projection on a 2-dimensional surface, right? So there's all these kinds of in-dimensional, like, kind of things like flatland. Like I read flatland, and like my math teacher made us all read flatland, and that was kind of a revolutionary idea that things could be projected on other things, or that there might be, you know,
higher levels of topology.
Right. What do you think of that, Jim?
Well, okay, so that is super interesting. And as a kid, I thought about you'd read about tesseracts and Wrinkle in Time and The Man Who Built a Crooked House and all these things that were kind of coming out in the 70s and the 80s. And you would think about them as complete and total abstractions. And then somebody I think it was Rudy Rucker who initially started saying, hey, look, if you want to understand higher n-dimensional geometry, right? Like, let's say we're starting with a point, then we have a line, then we have a square, for example, as 2D, then we have a cube as 3D, and then what if we took all those points and put them outside of themselves? That would be 4D, right? I said, well, it's really hard to understand what that might be. So let's go back to Flatland, which is the idea that you could have a universe that exists on a plane and everything that's seen by the occupants of Flatland looks like an edge. It looks like a line. But then when we, as people in the third dimension, look at it, we can see that they're seeing a cross section of three-dimensional space in what they're saying. And say, what if we in 3 dimensions, 3 spatial dimensions, lived in the equivalency of Flatland? And so all of these models then become
limited,
the equivalency of that, right? It becomes an extrapolation from that point. And there are other things, like we think about tesseracts, right? Like, a 4-dimensional cube, but there are all kinds of any shape that you can imagine, any kind of
soap bubble formations.
Oh yeah, like any
shapes like that.
Any kind of object that you can imagine, like a tetrahedron to a polyhedron, all these you take those and you turn them into n-dimensional geometry, and they're like the n-dimensional version of a tesseract. Now, and these things don't go into 4 dimensions; they go into infinite numbers of dimensions. And somebody might ask, why would I ever care about n-dimensional topology, even if I am a CGI artist? Okay.
It's only making your job harder, dude.
Let me tell you a crazy story. The images on the right-hand side are images taken from a video that I did with Beats Antique with my friend Ivan.
These are fractal systems, fractal generators.
They're 3D. They're 3D fractals. Okay, but here's the thing that's crazy about this. I was having problems with random geometry just popping into the view, and I started looking around through, the formulas that I was kind of putting together, and I realized the formulas were higher than 3-dimensional formulas. And so what would happen is the camera could not detect geometry sometimes because it has kind of a clipping plane, or else you can't see anything because it's just pure density, right?
Right.
And so the camera is actually doing something weird inside of the shader to clip through dimensions, right? And occasionally you would be going and then something would just pop out of thin air and would completely ruin the shot because you had no way to visualize this at all. And that's because inside of these fractal algorithms, they can use huge numbers of dimensions in order to create a topology.
Interesting.
Yeah.
So we're running out of time. So
okay.
We like to have a little bit of time at the end to talk about like implications and ideas and stuff. What coming out all this kind of like, what do you guys think this holds for the future, or holds for how we see the world? Or
well, I think there's a difference between like the concept of a dimension written by a science fiction writer versus the concept of a dimension written by a physicist. Like when you look at like Star Trek, Rick and Morty, there's a doorway and someone's walking through, and then suddenly it's some other place similar to what was going on there, and he's a person. And
yeah, Rick and Morty, they do that a lot. They have like doors that open to other places.
Yeah,
Wow.
but when you
Right.
look at like an actual like definition of a dimension, it's like, well, what is like depth compared to time? It's not just like France compared to Italy. It's like apples and oranges. I mean, there's no continuity,
Well,
really.
a lot of times when people say dimension, they mean multiverse. Like you're
Well,
not.
absolutely, absolutely. That
Yeah.
it's the definition of these terms
Like
that I think
like
is
quantum
important.
like quantum layers, like when there's a differentiation between a potential time, like even time stream or whatever, right?
Right. Dimensions are kind of more just a nuts and bolts way of describing the reality of something, not like it's just a
Well,
door
hey,
to a vacation world.
let me ask you guys about this. You always see something like a time machine, okay? And so somebody said, what would be the first thing that you would do if you had a time machine? And I said, the first thing I would do is start putting out buoys. And they're like, what? And I'm like, yeah, I'd start putting out buoys because there is no way to know where you are. And if you went into a time machine that was decoupled from space, what would happen is if you went back 2 minutes, you might end up hundreds of thousands or millions of miles away. And so the first thing that you need to do, if you have something that just works on the reference of time, is drop out a string of buoys to figure out how fast and which direction you're moving. Because one of the biggest questions you can ask is, how fast am I really going?
Well, I mean,
Right.
the
The
reality
whole
is
solar system
the,
is
the reality
in
is
yes.
if you are in a time machine and the only thing that's changing is time, you turn it even a second off, and the Earth is somewhere else. So
Yes.
there's all this stuff that isn't being tracked in those fictional versions.
Well, the only people who do that are, as this is a weird one. As much as I'm a latecomer, like when I was a kid, I watched Doctor Who, but later on, I was like, Doctor Who is the only one who says if you have a time machine, you have to have a machine that can travel through space as well.
Exactly.
Right? Oh, that's another one. The TARDIS is bigger on the inside than it is on the outside.
Well, like you look at
object.
You look at the modern models of the solar system. It's not a stationary sun with the planets going around it. It's the sun is moving and it's got the rest of the solar system in tow.
It's a corkscrew.
Yeah. So all these orbits are not ellipses or circles. They're all these wobbly spirals. So yes, if you were in the same spot 1 year from now, you'd be floating out in space going like, hey, there goes my ride.
Yeah, that's right.
Um,
okay, we got to wrap it up, guys. It's so great to have done this once again.
I'm loving it.
And what's coming up, not in the next show, but in upcoming shows, we're starting to look at inviting guests that either we've talked about or that we think are interesting. So that's coming up, and I'm really excited about it. I can't announce who yet until we get it all nailed down, but that's going to be really interesting and looking forward to it.
Yeah, that's going to be fun. That's going to be a lot of fun.
So great having another excellent show. Thanks a lot, you guys. And
oh yeah. Love to see you guys. Love to chat it up.
See you in the future.
All right. Bye-bye.